Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from Mahatma Gandhi, the father of nation, who says, happiness is when what you think, what you say and what you do are in harmony. All of us are running after getting happiness, and as if that is our birthright, but however we miss it all the time. So he has given a recipe, we need to follow that. And let us recall that what we learnt in the last lecture. In the last lecture, we basically looked at quasi one dimensional isentropic flow in a nozzle, or rather in a variable area duct, and derive a relationship between the area and velocity. And we have seen whole regime of the flow, starting from the incompressible flow, then subsonic, supersonic and also sonic flow, and we argued why a throat is required and why a diverging portion is required in a convergent divergent nozzle for getting supersonic velocity at the exit of nozzle. And today we will continue the discussion and trying to find out basically a relationship between area and Mach number. And let us look at a convergent nozzle. As I had told you earlier, let us assume that it is being connected to a reservoir, and with a pressure of PT2 and temperature of TT2 and V is equal to 0. Let us say this is your station 2 and this is your exit, and we are considering the flow to be such that, that means back pressure is such that this portion of the nozzle is basically choked. That means this area we consider as A star, and the properties will be rho star, P star, T star. And let us consider another place of arbitrary where we can consider is a rho area, velocity and also the pressure and temperature of all this region of any arbitrary. And for that, what we will be doing, we will be basically considering the continuity equation or the mass conservation equation. Mass conservation between one station, let us say this is your basically a station of the station here, I can say this is A and E. In this case we can say that this will be basically rho A V is equal to rho star A star and V star, and this star corresponding to the choked conditions, choked flow condition. Keep in mind that we say that at this point the nozzle is choked aerodynamically. Nozzle can also be choked thermally, but we are not considering that. We are only considering that the nozzle is aerodynamically choked. That means it has reached a Mach number equal to 1. That means the speed of the velocity at the exit or the in this convergent nozzle, at the exit of convergent nozzle is equal to the speed of sound. So, let us now find out a relationship between the area, any arbitrary area A, and with respect to the sonic condition or the choked mass flow condition, that is equal to A by A star is equal to rho star by rho and V star by V. And we are assuming the flow to be isentropic in nature. So, therefore, we will be using isentropic relationship between the density, between the temperature, between the pressure, whatever it is required. Let us say we know the T that is the total temperature, T is equal to 1 plus gamma minus 1 divided by 2 m square. Similarly, I can write down P T by P is equal to 1 plus gamma minus 1 2 m square gamma minus 1. Similarly, we can write down rho T by rho is equal to 1 plus gamma minus 1 2 m square 1 gamma minus 1. So, if I want to find out with the choked condition, I can get that very easily considering the Mach number to be 1 in this expression and find out choked density, choked mass flow rate, and with respect to of course the total. So, let us write down this as basically is equal to rho star by rho T. I can write down with respect to always with the stagnation condition into rho T by rho, and V star as I told is corresponding to the A star, that is the speed of sound, because Mach number is equal to 1. So, therefore, V star is equal to A star, I can say that because Mach number is equal to 1 and by V. And by using isentropic relationship, we can get basically rho star by rho T is equal to 1 over 1 plus gamma minus 2 into 1. I can write down that is basically 2, that means 2 by gamma plus 1 power to the 1 minus gamma minus 1. So, this itself will be, when you say 2 plus gamma minus 1, cancel it out, the gamma plus 1 divided by 2, that became 2 divided by gamma plus 1. Rho T by rho, I can use this expression directly, and let us look at this A star by V. If you look at A star, by definition the A star I can write down as root over gamma R T star, and divided by this V I can express in terms of Mach number, that is Mach number, and A I can write down as gamma R T. And keep in mind that this gamma R both the numerator and denominator can be cancel it out. I can get as 1 by m root over T star by T. By using this isentropic relationship, I can write down T star by T is equal to T star divided by T T into T T divided by T is equal to, if you look at T star by T T will be nothing but your 2 by gamma plus 1, because from this expression if I put this m is equal to 1, like for m is equal to 1, the T t by T star will be 1 plus gamma minus 1 divided by 2 will be basically gamma plus 1 divided by 2, and this is just opposite of that. So, therefore, it will become 2 divided by gamma plus 1 into I can use this expression, that is 1 plus gamma minus 1 divided by 2 m square. So, if I take this as equation A, then I can say this is B, right. I can use this as a C, and this expression also I can say this is basically C1, and these are expression for basically densities and other things we can use. Then equation B becomes A by A star is equal to rho star by rho t is nothing but your 2 by gamma plus 1 minus 1, and rho t by rho, if you look at, it will be 1 plus gamma minus 2 m square into A naught by V is basically 1 by m, and 2 by gamma plus 1 plus 2 m square root over. So, if you together put this thing, and then you will find that simplify that, you will get A by A star is equal to 2 gamma plus 1. I will just take this indices together. Let us put that thing. You can recognize this term is same as that. So, this is 1 plus I can say that this will be 1 minus gamma minus 1 plus half. So, that becomes basically, if I take this 2 and gamma minus 1, so that is equal to 2 plus gamma minus 1 divided by 2 into gamma minus 1, that is equal to basically gamma plus 1 divided by 2 gamma minus 1. With this I can write down this basically, this is the expression I can write down. Is equal to gamma plus 1 power 2 gamma minus 1. This is my expression for area and Mach number relationship, and this is, let us say this is D, and this is known as area Mach number relation. And interestingly, you can see that this area ratio, that means any cross sectional area in a nozzle with respect to the sonic area or the throat or the choked area, is dependent on the Mach number and also gamma. That means, in other words, you can say that Mach number at any location of a variable area duct is a function of area ratio, that is A by A star, always with respect to the choked condition, and gamma. And keep in mind that this area ratio, that means any cross sectional area, A will be A star greater than A star, A greater than A star is feasible, physically possible. Physically feasible, that we have already seen. That means the throat area should be the minimum as compared to other part of the nozzle or a diffuser or whatever it may be, and A cannot be less than A star. Physically not possible. Keep in mind that this already we have discussed, but now again this expression is also telling the same thing. But another interesting thing you can infer from this equation is that for the same area ratio you can have two solutions. That means one will be subsonic flow, other will be supersonic flow. For that, to appreciate that point, let us now plot the A by A star with respect to Mach number. This is your A by A star, and let us say this is your Mach number 1, and this is side is less than subsonic, and this side is basically supersonic flow. And if we will plot this one, you can see that this will be this is a solid line, and then you can have little and this solid line gamma is equal to 1.4 and dashed line correspond to gamma is equal to 1.2. So, you can see that this side is basically subsonic flow, and this is your solid line supersonic flow, and you can see that area, of course, the this side slope is little lower and this subsonic side it is little higher. But for a particular area ratio, if I consider, there are two solutions. One is here corresponding, this is basically subsonic flow and this is supersonic flow. So, that depends on the condition prevailing in the nozzle, that we will discuss in the next class. But another thing you should also look at is that this dashed line, that gamma plays a very minimal role. Of course, I have little bit exaggerated. Generally the difference between both the solution, particularly for supersonic flow, this variation will be there, and subsonic flow this won't be, but that this is this difference between the solution of this condition between the gamma 1.2 and 4 is quite less. So, with this we will stop over here, and in the next lecture we will be discussing about the flow resins in a convergent divergent nozzle or the de-Laval nozzle. And thank you very much, and we will discuss that in the next class.